Hello, everyone. So our group's topic is Chinese remainder theorem, and we have 4 members. I'm Jacinda Chen, and we also have Lucky Bao, Shirley Chen, and Serena Fang. So I'm going to start off the presentation with an introduction. So Chinese remainder theorem, known as CRT, was first discovered by Chinese mathematician Sun Zi, and it is a theorem which gives a very unique solution to simultaneous linear congruences with copine moduli. So basically, if one knows the remainder of Euclidean division of an integer n by several integers, then one can uniquely determine the remainder of division of n by the product of these integers. So in order to make that more understandable, I'm going to illustrate with the example shown in the slide. Suppose we want to solve for x when x equals to 2 mod 5 and when x equals to 3 mod 7. If we have a solution y, then y plus 35 is also a solution. And we got 35 by product of 5 and 7. So we only need to look for the solution mod 35. And by brute force, we can find that the only solution is x equals to 17 mod 35. Chinese remainder theorem is widely used for computing with large integers, since we can represent big numbers with an array of small integers. And this is known as Garner's algorithm, which will be later discussed by Shirley. And by the same logic, an interesting application of CRT in the design of computer software is that it breaks up a very complicated calculation into several less formidable calculations. It is also very useful on parallel processing computers, especially as they can run multiple programs at the same time. So now I'm going to talk about the algorithm of Chinese remainder theorem. And so to restate the definition, Chinese remainder theorem states that if m sub 1 until m sub k are pairwise relatively prime positive integers, and if a sub 1 to a sub k are any integers, then the simultaneous congruences shown in the picture in the slide have only a unique solution modulo m, and the m is the product of m sub 1 times until m sub k. After understanding the Chinese remainder theorem algorithm, I would like to introduce another consequence of CRT, which we can represent big numbers using an array of small integers. And this is the Garner's algorithm. And so, for example, let P be the product of the first 1,000 prime numbers. And from calculations, we can get that P has around 3,000 digits in total, which means it is a pretty large integer. And to calculate that, we can apply a formula, which is shown on the slide. And it states that A equals to x1 plus x2 times p2 and plus n2 xk times p1 until pk minus 1. And this formula is also called the mixed radix representation of A. And the Garner's algorithm computes the coefficient x1 until xk. I'm going to talk about the computing method of Garner's algorithm. Using the same example from the previous slide, we first denote R sub ij as the inverse of pi modulo pj. And this can be found using the algorithm described in modular inverse. And the modular inverse code will be explained in the future slide. And after that, we'll substitute A from the mixed radix representation into the second picture of this slide. And after that, we substitute into the third equation. And it can be rewritten by subtracting x1 and dividing by p1. And eventually we'll get the last formula shown on the slide.
The basic goal of our algorithm is to find a minimum positive number x that has the property shown in the picture. So on the right one is an example, which we have two arrays. The first one is the array of numbers, all the numbers in this array are pairwise relatively prime, which means pick any two numbers from the array, you'll find that their greatest common divisor is 1. And then we will have another array of remainders. As you can see in the expressions above, when x is divided by a number n, from the number array, it leaves a respective remainder from the remainder array. So for example, 11 is the smallest number such that we divide it by 3, we get remainder 2. We divide it by 4, we get 3. And we divide it by 5, we get remainder 1. We will introduce two Java implementations in this presentation. So the first one is a very simple and straightforward one, which is called native approach. The basic idea is to start with 1 and one by one increment it and check if dividing it with the given element in number array produces corresponding remainders in the remainder array. And once we find such an x, we return it. In the Java implementation, we write a method called findMainX, and we initialize the x of value 1, and we wrote a while loop, which is always true. We initialize an integer j, and as long as j is smaller than k, which is the length of the array, we continue the while loop and check if the divide the number from x match with the remainder. And if not, we increment x by 1 and continue the while loop. And if all remainders matched into arrays, then we found the x we want and we return x. This method has time complexity OM, and M is the product of all elements of number array, and it has space complexity O1. The second Java implementation is called the inverse modulo-based implementation, which is a more effective way. So at the up left corner of the picture, here's a formula which we will be used to calculate the x we want. And we will set 4 arrays. The first one is remainder array, which is the given array of remainders. The second one, prod, is the product of all given numbers. So in the example shown in the right, prod equals to 6, which comes from 3 times 4 times 5. And then the third array we are going to use is called pp, which is the product of all divided by none. So in the example, the first one, 20, comes from 60 divided by 3, 15 comes from 60 divided by 4, extra. And the fourth array is the inverse array, which we have a way to calculate it. For example, the 2 comes from 20 times 2 more 3 equals 1. So we need to set all of those equals to 1 and get the number we want. And we have specific Java code to implement that. And eventually, we calculate x from all those arrays we get from the previous code. And eventually, we got 11 in these examples. The following Java code is doing exactly what I described in the previous slide. So the first method is the inv, which will return the inverse array we are going to use for calculating the final result of x. And then we apply a method called findMainX, which will calculate the prod integer, the pp integer we described before, and eventually it will return the x value we want. This method have time complexity n log n with space complexity O1.
Then I'll discuss some of the applications of the Chinese remainder theorem. Since ancient China, people have adopted this theorem in broad range of applications, such as calendar calculation, war building, soldier accounting, and secrets sharing. As mentioned in the introduction, Chinese remainder theorem is first introduced in Sun Zi Cun Jing to solve a problem with specific numbers. For example, the classic problem is about counting things. The question goes, there are certain things whose number is unknown. If we count them by 3s, we have 2 left over. By 5s, we have 3 left over. And by 7s, 2 are left over. So how many things are there? Since ancient China, people mainly use the Chinese remainder theorem to calculate the calendar. Specifically, they use a theorem to find the years that have a certain period number with respect to the solar and lunar cycle, and the Roman indiction with the product of the different cycle days. Later, this kind of computation was also used in building a wall or the base of a house, such as the construction of the Great Wall. For example, to construct a rectangular base for a building, there are 4 kinds of materials available, and we have to use these 4 materials without breaking any of them into little pieces. Therefore, we utilize a system of congruences to calculate different materials usage and cumulative length in building. Moreover, the algorithm is also used to compute the number of soldiers that went out for battles. To avoid the enemy of knowing the exact number of soldiers he has, a general would use this theorem to counter his soldiers. For example, he may ask his soldiers to line up in rows of 11, then in rows of 17, 29, and 31. Each time the general is reported with a corresponding remainder, and he will use all of the remainder to calculate total number of soldiers with the theorem. This theorem is also used for later range ambiguity resolution. For samples of different range locations, the theorem combines the range intervals and remainders to find the true radar target distance. There are also advanced applications of Chinese remainder theorem. First, for any finite sequence of integers, we can find another 2 integers to represent it. The theorem can also be used to calculate the that-kind domain in which each ideal can be written as a product of a finite number of prime ideals. Lastly, Chinese remainder theorem can also be applied in secret sharing, which is an important topic of cryptography. Each party that shares the secret may have a specific residue regarding the prime positive integers encoding the secrets. Then the Chinese remainder theorem is used to decipher those pieces of information and determine the original secret scheme. That's the main applications of our Chinese remainder theorem. And thanks for watching.